I am John Gulliver, and I will introduce the speaker and our seminar series. This series of seminars is co-sponsored by the Water Resources Center and the St. Anthony Falls Laboratory, both at the University of Minnesota. The funding for this seminar comes from the Minnesota Stormwater Research Council. Our speaker today is Dr. Shirley Clark, who is a professor of environmental engineering and chair of civil construction and environmental engineering at Pennsylvania State University, Harrisburg. Shirley received a BS in chemical engineering at Washington University in St. Louis, an MS in civil engineering, and a PhD in environmental health engineering at the University of Alabama at Birmingham, where she worked with the legendary, at least in stormwater circles, Bob Pitt. I don't know if Bob is watching us today, but yeah. The next paragraph came out of Shirley's website, and it's just a beautiful paragraph, so I'm just going to read it as is. Shirley's research focuses on the challenge that society faces with the stress of urban growth and decaying infrastructure intersecting with climate change in vulnerable communities. She started her research career in the area of optimizing urban stormwater treatment devices to protect receiving water from the myriad of stormwater pollutants, including solids, oils, metals, nutrients, and bacteria. As climate change has produced more intense storms and longer dry periods between storms, her research has expanded to address the impacts of these changing water regimes on pollutant capture and retention in filtration-based systems. And that could describe, does a beautiful job of describing all of us in stormwater research. So thank you. I'm not going to steal it. Shirley has been very active in professional societies, most recently as president of ASCE's Environmental and Water Resources Institute, and that is a job and a half, serving 26,000 members of the Institute. Also noteworthy is her service on the Pennsylvania Department of Environmental Protection's Water Resources Advisory Committee and on the Chesapeake Bay Science and Technical Advisory Committee. So please join me in welcoming Dr. Shirley Clark.
Okay, good. This went to green. We should be good. Thank you, John. I don't know who found my website, but I need to make sure I hide that part of it again. Okay, so I'll go ahead and get started, and we can have the time for Q&A at the end. I do want to upfront credit actually somebody who came up with a title. Because Andy asked me for a catchy title that would get attention, and one of those let's be an engineer nerd moods, and couldn't come up with something. So I'd like to credit this title to Bing AI. After 2 iterations, it came up with the title, but that is the only thing in this presentation that artificial intelligence has done. Everything else has been the result of many, many years of hard work by me and my students. So again, I would put them on the front page. Some of the, you'll see them at the end, as many as I could remember. But if I put everybody on here, we'd be at about a 2-point type, and we couldn't see anything. So I do want to start with that. So again, I know some of this came off of discussions we're having around our Lancaster research area. So we all know what we find: a parking lot, somebody comes in, it may be government regulators, it may be some of our manufacturers in there, and we need to treat the runoff from that parking lot. So we get a treatment device, and then they go away, it rains, we get runoff, sun comes out, and out the backside comes this lovely treated or clean water. And somehow, some way, this all magically happens. You know, so again, we've got a lot of guidance out there that's been written by researchers primarily that delve into this, but really the regulatory agencies have some very generic guidance that's available. My state, it says, well, you can expect a device to remove 85% of phosphorus. Okay, with very little specification on how we're going to accomplish that. So what I want to do today is look behind the curtain a little bit, and this is going to be a very high level introduction to this. This talk could easily be 8 to 10 hours, but what we know is that we have a lot of different processes going on inside these systems. And I'm going to stay with filtration, biofiltration, bioretention as the topic talk. But again, and this is not well represented in any of our stormwater models, is how these different processes act, interact, et cetera. so we can understand and how we can reduce the high variability in results that we get. We might look at a single site and find that the variability of effluent concentrations are very low. We take this across the nation and look at like the BMP database. Those are orders of magnitude. And so how do we understand what's going on, better model what's going on so that we can begin to narrow that range out of orders of magnitude into maybe an order of magnitude or an order of magnitude and a half. First statement, what goes in is an issue. So first of all, I'm going to come in and take a look at various ranges of particle size distribution for our suspended solids. The red line is if we want to get 50% out. The purple on the bottom is if we want to get 90% out. If you look at it, if we're going to get 90% of our total suspended solids out of our stormwater runoff in a residential area, we're looking at having to remove 1 to 2 microns. That's not going to be done by sedimentation. So we're really looking at having to filter. We start getting into our dissolved fraction. We start thinking about what is it? And so they told me that's the button. Yes. So if you look up here, for example, this is a project we were working on out in California, and the solid bars are a metal. You can see them down here. And the crosshatches are the concentrations that pass through the 0.45 micron filter. But take a look. For this one, it's fairly far apart. Look at that. The bulk of that metal's concentration is in that dissolved fraction, which means that we got a different level of treatment. It's not going to come out by straining or filtration physically. So we came back in and said, what have we got? So in this case, we came down and we actually hit this with UV light. And you can see the concentration for some runoff collected outside and the metals concentration, and the metals concentration went up when we actually hit it with UV light. We're actually getting, once we get away from it being bound to organic matter, the metals concentration goes up. Because again, most of the test methods don't pick it up in organic matter unless you're going into a true lab and dissolving it. But if you go outside with a field monitor, you may miss it. So we look at it, the data comes in and says, how much is ionic and how much is bound? And they are different by metal. They're very different by metal. And that does affect our metals treatability. So the next thing we did was we started modeling that. This doesn't have the DOM in it. But if you look at it, how much in there is by different valence charges? Remember basic chemistry, the one that says you have to go +2, +1, -1? So that we'll just kind of refresh that college chemistry. And again, but look at the distribution. This is between copper and zinc. And again, this is modeled. But that's what's going on. We've got all sorts of interactions happening in the rainwater itself. And I put this up. This is actually the raw results of the modeling. And I don't want to highlight on any piece of it except that look at, if I can come in, if you look at the extensions coming down here, they're also complexing with the nutrients. So we're actually getting in stormwater runoff our nutrient metal complexes. They are not, again, the single dissolved metal that's a little small metal with a +2 charge, but we're also tying up the nutrients. How is this affecting treatment when we're expecting, and we treat these things and we think about these things in runoff as being a little ion with a charge on it? If I go back, I'm going to go back here. There's a lot out here. Okay, did I press the right? No, I pressed the wrong button. Let's get that one. There's a lot out here with no charge. We're using anything where we're expecting ion exchange, zeolites, where we're doing a charge thing. We're going to have problems because some of that's tied up in something that can't be grabbed by a charge difference. It affects a lot of our treatabilities. A lot of our media also rely on charge differences to attract and hold on to pollutants. So I'm going to throw this up here. We also don't talk about, when we talk about removing organics, we don't talk about the properties of organics. We're talking about how well does it absorb to organic matter and how well does it stay in the water? Where does it want to be? I should not anthropomorphize pollutants because again, they really don't have a want or not, but it's easy to say that. We look at, and this is a project, you look at, I'm going to get the right button. If you look at Deicing, very heavily wants to stick to organic matter, is very low in solubility, again, particularly for the octachloroisomers. But if we go down here and look at perchlorate, very low KOW, wants to stick to organic matter, but fairly high solubility. And then again, coming down here to dimethyl mercury. So think about it. Where does the pollutant want to be? Does it have the charge? Does it have the capacity? Does it want to stay where it is? And this is nowhere we think about. Everybody's like, oh, runoff's runoff. And that's a bit of a challenge. I mean, we might say, oh, this industrial runoff's different than the residential runoff because it might be the difference in pesticides, fertilizers, metal sources. but we don't think about how what's going on in that, what its chemistry is, affects what's going on in treatment. So we'll skip ahead. Let's go to the filter media. So it's about the water. Oh, it's also about the filter. And we know with that, if we're going to do physical straining, then we are going to be in that 20 to 1 micron range, but all of our pollutants are out here. So really, we need a biochemically active media. And that's what we've been doing with bioretention and why I think they asked me to come up here and talk. So what do we need to consider? We need to consider all of these things. Soil and water pH, our pollutant forms, which I just went through, cation and anion exchange capacity, mineral, organics, phosphorus. Is it oxidizing or reducing? And then if we have selenium and sodium, again, and timing. It is a function of kinetics. We don't have enough contact time in our media, we will not get the removal we want. So that balances out the need to get flow through with the ideas. We go to a lot more sand versus what do we need inside the media, and we need to slow it down so we get that contact time. So also we come through a debate and we saw a lot of push towards putting compost in media. Well, what are the impacts of putting compost in? So we looked at this with a natural soil. We have our soil horizon, our organic soil horizon. That's on my soil concentration. My A horizon, the top soil range after the organics pulled off. It's a little bit harder. Influent quality. There's my effluent. There is a substantial difference by almost an order of magnitude if I actually have a lower P content in my media. Because again, it means that there's less phosphorus available to leach out. So I have to be thinking about what's that mix in there. But again, if I'm going to grow plants, I need phosphorus. If I'm going to do other things, I need phosphorus. And again, these are a lot of trade-offs and a multi-parameter optimization activity to be looking at what these should be. We also need to think about, this was one surprisingly, I had no idea, but I always show this because when we went out and collected soil columns, one of them actually shrank and came away from the edges. And so in order to avoid bypassing, we had to break it apart and rebuild the column. They're basically soil cores. The one on the right wasn't rebuilt. The one on the left was. Here's total nitrogen. That first flush was, again, an order of magnitude plus higher. So that initial first flush, if we break it apart, we start breaking soil bonds, some of our soil chemistry bonds, we are going to release nutrients and get very, very high first flushes that do eventually settle down, but we need to be prepared for that type of thing. So the more we mix up and break up soil and media, the more likely we are to have some very high first flushes when we first build these things. And I also came in, we took a look at it. What is that if we take a look at it coming across the percent of carbon and the percent of phosphorus? So the top one is going to be the, I'm going to look at, make sure. I should put on my glasses. This is the percent of carbon. The black dots are actually phosphorus removal as a function of percent carbon. As carbon goes up, phosphorus removal goes down. This is the ratio of effluent over influent. Now the percent of phosphorus in the media, it comes up. Again, phosphorus is a function of phosphorus. We see that leaching. So the more phosphorus in the media, the poorer the effluent quality, the less phosphorus we're going to retain. Makes sense. We're basically saturating the system. The metals don't have a huge amount of change, except for a couple of them we start getting out to about 6 to 10% of phosphorus or carbon in the media. So again, it's that argument again for being very careful between what is the organic matter we need to grow plants, and if we put too much in there, then we're going to have a problem with nutrient and metals capture, but particularly nutrient capture, particularly phosphorus capture. And there's a lot of work going on up here around iron amended soils and iron amended media we were talking about last night. What's growing in these in spite of the fact they're not planted? You know, what are the things we can do that we could potentially stabilize some of these things? So I'm going to give you an example. This is a really neat example. We were doing a project in California. It's the only project I've ever done where the permit required us to look at radionuclides. You've never had to design bioretention to remove uranium? Got a project for you. Yeah, and then of course I don't live far from 3 Mile Island, and my colleague asked me, Bob asked me, well, if you can't add it to the water for environmental health and safety reasons, can you ask 3 Mile Island to burp? I'm like, I don't think I can do that either. Probably not allowed. But let me give you an example here. This is going to focus on copper, but the permit we were dealing with had to deal with uranium, strontium, radium, thallium, antimony, nitrate, or total nitrogen, total phosphorus, E. coli, I know I'm missing, dioxin. Those are the big guys, mercury and mercury. Again, we had to remove dioxin down to 2 × 10⁻⁸ micrograms per liter. But I'm going to focus on copper because it's a really good illustrative example of the trade-offs. So the y-axis is going to be, push the right button, is effluent over influent. So again, effluent over influent at 1.0 means we got no removal. And if we get down to 0.2, we're 80% removal or 20% remaining. So this is, again, a granular activated carbon. And you can see across the loading what we got. Peat moss, rhyolite. I did, if it went above it, we have the 1-to-1 line. Rhyolite's in a surface amended sand out of the west, and then a surface modified zeolite. If you take a look at that, what you can see at that point is we've got really good results with our granular activated carbon. Challenge, it's expensive. Also, we did get some decent results with peat moss. Surprisingly, and this will go back to emphasize what I said about the water, we got really poor results with the surface modified zeolite. You can see that with this last one on the right. Why? Zeolite is designed to remove ionic compounds, but you saw with the complexation and the modeling, it's not ionic. We can't treat the metals like they are in pure ionic form and assume that these things are going to work. So one reason why we see better results in things like peat moss compost and others than we see in zeolites, because there's a multitude of binding sites on the outside of the media. So that's what we're really looking at. So now we do that again, so you can see what went on. Again, GACs and peat moss have a lot of different types of sites. So it provides a lot of different ways that this copper complexes could bond to the media itself. So we went in and started looking at mixes. And we came in, what we found was, of course, we mixed in the sand, the surface modified sand with the surface modified zeolite, didn't do real well. We added a little bit of GAC. Yeah, we did pretty well. Peat moss, we still got removal, not as good as the GAC. You can look at the y-axis and see. But we actually did that. We added the peat moss back in because peat moss did better for antimony. So this is copper, but I had to look at a multi-optimization question because every time the permit was violated, every time they had a storm, they had to measure. Permit was violated, it was a $10,000 fine. So we had to come up with some way to try to get everything. They actually did a good job. It's out there published, but just kind of to give you that idea of that thought process to come in for what are these multitude of pollutants. We are seeing a lot of permits. Pennsylvania has plenty of them. It's like we're writing them for suspended solids, nitrogen and phosphorus, but we're not writing it for other things. The federal industrial stormwater permit writes it for a few things, but not for a lot of mix of pollutants. So I wanted to throw that out there. This is really an optimization design. What's the impact of a biological community? We were talking about that yesterday with John and talking about biofilms. So this was actually looking at a scrap, this was as a potential green roof media. We're looking at a scrap tire, a shredded tire as a base to replace expanded shale to get a much lower cost, lower energy, lower carbon footprint, and also then putting in either a compost or a biosolids. And the real thing I want to highlight on this one just is the difference between the orange and the green lines. The orange is one where we did not actually spike it with E. coli, or sorry, the green one we did not spike with E. coli. The orange one we did, and that's our effluent concentration. So the biology makes a big difference. This is my microbiologist running this. So again, we know these systems are going to be active biologically, and we want them to be active biologically because the biology helps us out. The organisms help us out by taking it up. So again, taking up a lot of the nutrients. You can see that again, we went from having nutrient problems in our runoff. We actually encourage the biological community, maybe even spike it or irrigate with a treated wastewater. We could actually pick up some additional benefits in nutrient removal and reduce nutrient leaching. I do want to, before I come out of this, actually also mention though that we are seeing climate change. I am very fortunately up here in a long sleeve shirt and jacket, escaping a heat dome over the central Pennsylvania. I think today it's going to be either 96 or 98. I'm not sure which, but boy, I'm going to love landing in DC tomorrow. It'd be a very lovely walk to the car. So we did some things in there, and what's going to happen, what we're seeing, even up in Pennsylvania, we're seeing 3 and 4 weeks without rain. Not that often, maybe once or twice a year, but we're starting to see 3 and 4 weeks without rain. It has multiple impacts. One, obviously the plants are looking for the water. Most of our systems are not set up to irrigate. We're not set up to manually go out and irrigate our bioretention systems. And that's stressing the plants. But on the second side of it also is what's going on in the pore water, the soil pore water chemistry, because dry is not dry. We think about it may not be draining out water, but these systems hold water. That's why we have terms called like wilting point, that we do that. So we actually tried to drive things anaerobic and putting them in a bottle where we were on a shaker table, and we let them sit for 21 to 28 days. On the good side for us, in general over here, the metals held on really well. We weren't seeing a flush of the metals. But we started seeing on the organics, we started seeing a release of organics when the system went anaerobic. So what it means is that as we get into our first flush, it's been a little while since we actually got rain to continue to send aerated water into the systems and also keep the system flushing through, we're going to see a slug coming out. Again, that's just going to be what ends up happening. And this is going to happen more and more as we start seeing what's going to happen in climate change, which is highly variable weather. Where we're likely to see, at least in my part of the country, and I still think probably in the Midwest, although I think the models are not quite as extreme as ours are, is flash flood and flash drought. So we're actually seriously thinking about flash drought conditions and what impact that's going to have on the systems themselves if these things sit for a while. Again, what do we need to do to redesign? Oh yeah, it's geography. I forgot to put in last night the plant hardiness zones. We all know the plant hardiness zone shifted a little bit. And so Pennsylvania, we got rid of one of the colder sets. Basically, the colder part of Pennsylvania has now gone a little bit warmer. So it's all geography. And of course, I live in an area where we apply road salt, de-icing salts. We are seeing in Pennsylvania, and I suspect we're going to see this across the Midwest also, we are seeing potentially less snow, but we're not seeing a decrease in salt because we're seeing more ice. And in fact, for a lot of people, ice is actually scarier. But it doesn't change the salt loading, because what they've really got to try to do, because people get killed in ice. Not they don't get killed in snow, but really ice and black ice are really a challenge. So we're seeing our municipalities continuing to heavily salt in there, and they're washing into all of our happy little bioretention systems. So we've come in and taken a look at this in a couple of different ways. Very top, these are both flow rates. So on the top, and that's not the right one, that's the right one, is one we did in our lab, and that is, again, soil only in there, and then we added a compost to it. The flow rate decreased a lot faster when we had an organic piece in there. That's not showing up in the literature. If you go in the ag literature, which is where we started looking at where we could find data on what happens when you salt soils, because the ag people have been doing it for years. What happens when you salt soils is that we talking about changes in the soil chemistry. The soil seals, it bonds together, and effectively it acts like cement. It's all been blamed on soils. It's blamed on clay content. Organic hasn't shown up, but we're seeing it with the organic content. So Bob actually came down here with his students and ran the bottom one. And here, that's the bottom, was the exact same experiment, but he also did peat and clay. And what we really saw is this combination of peat and clay saw a substantial decrease in flow rate. So what does that mean? That's not just in the winter. If these things actually chemically seal the surface of the soils, that means they're not going to recover in the spring. So these are the things we're taking a look at, that what we planned for infiltration rates may be going away, in addition to the concern around, are your plants able to handle salt? So what does it mean? So if you're an industrial engineer, does anybody else in here do industrial engineering? Okay, so if you think about these filters, industry's been looking at these things for years. They're industrial resins. That's where I came at it from. These are industrial resins. This is what we do to clean up systems in an industry. This is what the chemical engineering degree I got paid for. How do you clean a resin so you can reuse it? You flush a lot of salt at it. So what you do when you flush a lot of salt at it, salt is a weaker valence charge, but at very high concentrations, it will still dislodge and flush into the effluent water, the concentrate. It'll flush out what's been captured, like metals. It'll flush it down. That's what it's due. So what are we doing every winter? We're washing our media. We're just treating it like a good industrial resin, and we're cleaning it off so we have it ready for next year. We don't think about it that way, which does mean that the metals start migrating down very slowly. But it also means that we think about it, it's not capturing what we want. So we did this is lab experiments. And what you can see, and we did look at multiple salts, so that's on the graphs. So we looked at, get the buttons right. Andy, I will get the buttons right somewhere before this presentation ends. There's our control. There are different salts. We've been trying to look at sodium chloride, sodium acetate, calcium chloride, calcium acetate, because some people are talking about, using an organic like a denatured beet juice, which is still very heavily organic, and that to look at those changes. But this is just really going to focus on the sodium chloride part. And you can see in here, after our artificial stormwater application, just overall through that time, we were picking up about 0.6 milligrams of metal per kilogram of soil after each dosing event for copper, 0.32 for zinc. But after the sodium chloride application, look at that drop. Copper's cut in half. So if we had copper coming up for our car, going to our bioretention, at the same time, we'll also have road salt. The uptake is smaller, and in zinc, it actually washes off. So we're looking at that and saying, in the winter, we are not getting the pollutant retention we planned on. In addition to cleaning it, we're just not getting the uptake. So that changes our uptake rates. So again, winter removal, because again, while salt is a weaker competition in terms of ion exchange, it is also there at much higher concentrations, and it just simply outcompetes. It's like having those Call of games that they keep advertising on there, where you've got one little guy with a shooter and it's being overrun by a horde of people. At some point, you just can't compete. So you got to look at it that way. So we actually have been out doing this monitoring in Lancaster, Pennsylvania. I want to thank my colleagues in Lancaster for letting us go play in their rain gardens. So we did put out soil sensors that are giving us continuous data for several years on salinity, or basically electrical conductivity in the soil. We also had some flow meter, some pressure transducers out there, the water sensor, as well as soil moisture. But this is going to focus on electrical conductivity. And what I want you to see with that, you can see up here, the different types of precipitation where we went through. This was the one year we actually had it recently. And here was roughly their salt application, and there's a delay until we see a response. So again, the salt slug moves when we get enough water or rain to actually move it off the street. We might pile it on the side, but there's a time delay on that coming through. We also saw on days where we actually got it cycling above and below freezing, we get a little bit of snow melt trickling into the system, we get a reaction, and then suddenly it freezes again. So we actually got some diurnal cycling, and you can see in there, for example, coming through here, just look at that decrease over time. But that is not because we got more precipitation or somebody went out and washed off the road. That's just because of the freeze-thaw cycle coming through the system. So you can begin to see that freeze-thaw cycle coming through. So, and we look at comparing two different winters. Again, they each had three salt events, about half the snow in the second year. The top one is the first winter, the bottom one on the right is the second winter. It's a little harder to see, but because we had a lot more time above freezing right after an event, it washed off a lot faster. And you definitely see the timing to the time of rain. You really need rain as opposed to higher temperatures. This is also had a top level conductivity about 5.5 on the right, millisiemens per centimeter, whereas the other one was about 4.5. They're all very high. And again, what we really saw was just that change, and then the tapering off. That was our last salt application, but you can begin to see that we're starting to see responses all the way out into April. So our response, our last snow event, they salted on, unless people did their sidewalks that we don't have records of, but the city did not salt after February 1st. And we're still seeing a response in the system almost up through April. What's happening in April? The plants are trying to grow. We're now in the fact we're getting into spring, and we're starting to see the plants trying to grow. Now, we did do the same thing on a pond on our campus. This is COVID. I'm going to say that in a reason. This is actually a more natural soil with a higher organic content. The Lancaster systems are a fairly sandy mix on top of a sand base layer. This is on a natural soil with a higher organic content. And you can see that none of this is that nice sharp peak. Because again, once you get in there, you have the salt reacting with these soils, and it's a much slower activation and release, particularly release. Again, so it's a lot slower to clean the salt off. And in fact, we're going out much farther. And you can see from here, there's our background in the fall. Even at the middle of March, we haven't gotten anywhere down near background. Now we'll say the tadpoles don't seem to be that disturbed with it. But again, the fact the higher the organic, the longer the reaction with salt's going to go, the longer it takes to flush it out. So again, this is a multi-parameter optimization activity that you all are doing. And we did take a look at that in terms of loading. We've got a high salt loading basin and a low salt loading basin that are in the same treatment train. And so again, with that, we have, again, surprisingly, these are nutrients coming through. There's some things we don't totally understand. We don't understand why the low basin had a higher flush out of nutrients as opposed to the high basin. So I will say there's still data we don't understand either. Again, we just don't understand because the phosphorus, we actually got decent removal. So, oh yeah, and it's the plants. So I just want to make sure as I start this, let me acknowledge a couple of things. One, this was Dr. Goch's undergraduate class. Did this as part of kind of a capstone type activity. They were incredibly dedicated. I don't know that I can say that enough. Most of these kids don't have cars. We gave them about 20 basins. They want to do almost everything in the city. They did about 100 basins. They hauled equipment on bicycles around the city. I mean, and they were out there at 2 a.m. That was not part of their class requirement. It was all told, be safe, don't go out at night, whatever. We would turn around and there's data coming back in from 2 a.m. So I want to acknowledge the impact of good students. And again, a good group of undergrads and what they came up with. And this is published. I thought it was open access. It's not. If anybody wants the article, at the end, I've got my contact information. You can email me and I'll send it to you. This is they looked at 100 basins, over 100 basins in the city. And interestingly, they actually measured area. They got a lot of that off mapping, but they looked at different types of plants that were in the different basins and the number of species. So there's still some additional analysis we would like to do, but I just want to give you an idea for kind of that feel for what we have for data at this point. Just to give you an idea of the parameters, they went out and measured all of these parameters in all of these basins. Most basins they did only hit once. Some of them they did hit a couple of different times, but just to give you an idea of what's out there, of what we had. There's our seasonal comparison of nutrient removal. Again, you can see as we would expect in the summer, again, across the basin from our, in through the center to the out. But we don't see that difference in the, let's get the buttons right. We don't see it in the winter, but we actually don't see the out. We just didn't get anything coming out of the basins, even in the winter rains that much in the basins that we were looking at. So again, what is really interesting to note, though, I'm going to come back in here, in the summer, why do we get that reduction? It's very likely it's some reaction with the media, but it is the reaction with the plants. We've got growing plants, plant uptake as we would expect. No change in the winter in the basin itself, even though we have no outflow, no plants. They basically come in and harvest out the biomass, typically in the late fall. And so they actually cut everything down to start over again. Now, seasonal impacts. This was actually a really interesting one to try to figure out the data. So again, summer, winter, left, right. On the top part of it, we have our soil electrical conductivity. Come up here. That's what we'd expect. Put road salt on it, get a higher electrical conductivity. Again, we come back in, interestingly, as we would expect, higher infiltration rates in the summer, growing plants, less salt, root penetration. We should get higher infiltration rates. But some of the things we've been looking at is that we've been thinking about, does compaction or other cheap measures tell us if they're failing? Our compaction layer actually is, we're basically at 100 PSI at about 3 to 6 inches down. Up here, we're closer to 200, 150 to 200 in the summer. Why? Root mass. Again, that root mass gets very dense in the system, and it's very hard to get a cone penetrometer through. So you would think that usually we think about compaction, we're thinking about soils that are failing or systems that are failing. That actually may be a sign that it's actually working, that we're getting that penetration because we're getting a good root mass and a good habitat. And again, you can see in here, then looking at soil moisture. Okay, come on. Did I just use up all the batteries? Maybe have. But anyway, I'm not going to worry about it. So at that point, on the bottom right, I'm almost done. You'll see that in the winter, the soil moisture was actually higher, which we would expect. We don't get as much drainage, but also the plants are taking up the water. So we actually, again, it's the benefit of the benefit of the water of the plants themselves. And yeah. Oh, so there it goes. I want to highlight that one where we talk about the infiltration rate coming in. There we go. We've been trying to plot this a little bit to look at the interaction of moisture content and electrical conductivity. And of course, because the infiltration rate determines that contact time, which affects the kinetics. And as you can see with that, again, when the soil moisture is low, again, we do see a much higher infiltration rate, as we would expect. There's room in there to put water. There's air pocket space to put water. But we have to think about what that interaction could be, and then, of course, how it ties back in. Future analysis to look at this in relation back to that chemistry data that you saw. It's the plants. I just want to make sure I close with that. It's the plants. So you can see in here that we have, and then I have to put the glasses on so I can actually see everything. The water content, I'm just going to do this again. Oh, I did go. Okay. So number of species versus water content. These are all, although they're highly variable, these are all statistically significant. As we would expect, as the water content goes up, or the species goes up, the water content goes up, they're holding moisture. On the right, on the top right, then we're looking at water content and canopy height. Makes sense. You've got the canopy, you've got the water, you can grow the plants up higher. Interestingly, I want to make sure I'm very clear on the bottom one, because I think that it does get missed a little bit. We actually saw an increase with electrical conductivity and the plant number and the number of species. Note the number is not very high. That's not winter numbers. That's 200 microsiemens, not, and we were in the winter, we're at 5.5 millisiemens. But why? What's likely happening at this point, this is not road salt. Those are minerals and nutrients, because electrical conductivity is not going to distinguish between what it is. So that's likely the fertilizer, the nitrates, the phosphates that the plants are taking up. So that's actually good to, that's good to have that low of an electrical conductivity. We don't want zero. What about climate change? And I put this one in. We're doing a little bit of analysis with the BMP database, and this is the total nitrogen. What I want to show, obviously, it's highly variable with removal. This is the red line is the no removal line. But as we start getting out here above about 3.5 to 4 inches, we start seeing an envelope almost up here. We start seeing an envelope that we're not going to get better removal. So again, this is the BMP database, all the studies that are submitted. It may be we're triggering the bypass. So again, measuring effluent, that's going to be the bypass water plus potentially the treated water. We also could be trying to force water through these things faster, and we could be getting less contact time. It's an envelope. It's a very quick analysis. The really good storms are not being measured because they're not regulatory storms. Those very high storms where people like, my equipment washes away, so we're going to take it out, or we're not going to do it. But it is thing to think about. Are we going to start seeing a cap in the performance that's less than what we're predicting as we start trying to put more water through these systems? Not because we designed for it, but because we didn't design for it. Because we aren't accounting for climate change and a lot of things. And all of us are now scrambling to figure out, how do we incorporate climate change into these designs in a way that is defensible to our clients and to the regulators? So my closing thoughts: bioretention. It's a multi-factor optimization exercise. It's the water, it's the media, it's the plants, it's where you are. Lancaster, for example, tried to put in native plants. They did very native to their region. Road salt killed them. So they decided native plants actually extended to the Jersey coast. Seriously, they put in salt tolerant plants. Well, it's the same latitude, same hardiness zone. It's just a difference of 100 miles or so. Again, the kinetics are important. Kinetics of removal are important. So again, that design of contact time is important. We're trying to get around it with a lot of the good research of people who are in this room, who are online, who you've heard from in past seminar series speakers, with this idea of, we design it with this media mix and this set of components, we're going to get good removal. And why are we doing that? Because it's affecting the flow rate, it's affecting the chemistry, it's affecting the contact time. Now, but people go in, well, what if I put more sand in? We change that, then these things change performance. So again, it's understanding what the processes are behind it. We do need about 5 to 10 minutes. Plants are vital, but we don't know how to design. At least when I run swim for an LID, it'll ask me if I want certain plants, but it doesn't give me a lot of help in there about knowing what the plant's going to uptake, what's it going to do. They just kind of assume vegetated or not, or maybe grasses or something. Even Winsland, which is focused a lot on this, still like, well, you're going to have turf grass, you're going to have shrubs or what. It's not, nothing's that far into understanding. And you'll be hearing, we got people in the panel who are much better at plants than I am. I kill, not in a good way. But that, that can talk about what the plants do, and different plants do different things. Some things are better in certain situations than others. And what I'd say is, closing it out, there's still that issue of winter road salt and de-icing. That's not going to change. And as the ice line shifts, we're going to see more of that. Not a lot of people talk about the fact that as temperatures warm and we're moving north, that there's actually still an ice line between what's going to primarily be rain and what's primarily going to be snow. We have to deal with that. And then there's climate change. So I'm going to throw that out there. This is the ones I could remember. And this is these are my big researchers, but there are plenty of others and plenty of people I'm going to apologize for not acknowledging at this point. So again, you can see in there. And last stuff, if you want to get in touch with me, there's a QR code, there's my email address. Also, as the last piece, and John had mentioned, I'm president of EWI this year. We're actually having a workshop with NOAA next week to talk about the technical needs for precipitation or climate data. If you would like it all to participate in a survey, that's the bottom link. Feel free to take that, QR code it, whatever. We would love to hear from you. I'm trying to take what people are saying in this community back to NOAA to help them prioritize what data we need and when. They got an infusion of money that they have to prioritize. They don't have the people to do everything immediately at once. But if you had to ask for data needs, what would you be asking for and how? So I'll leave it at that.
So that was a lot of information. Very, well, actually very good information. I was surprised by some of your results, but let's ask the audience if they have any questions.
Really wonderful presentation, Shirley. One of the assumptions was in the summertime, you had higher infiltration rates, supposedly due to the root mass in that. But was there any consideration for the soil invertebrates, worms, insects, things like that, that are burrowing and likely much more in the summer when they're
I would agree with you. Absolutely. We did not look at them. We did not have, the team had somebody who did plants and did not do earthworms, et cetera. And you're absolutely right. I should have included those in there. I'm a chemical engineer. That's biota. But no, in all seriousness, there's a teaming community going in there, you know, from bacteriological to rhizome roots structures to bugs, all that. So absolutely. The Lancaster mix is a little interesting. I've dug into it. I haven't seen a huge number of worms because it's a more sandy mix, but that doesn't mean they aren't there and they don't scurry away when they're like, oh crap, here comes that person with a shovel. Soil core. So, we've seen a little bit in there. Not as much as I would see in my pond digging out where it's a much higher organic content. That also has tadpoles and other things in the standing water. But absolutely, we have to include the organisms that are likely to be more prevalent and more active. Because in the summer, of course, they're going to go through a cycle where they would be, hatching new and then, through whatever mechanism and then coming back out. Absolutely.
Do we have a question from online? No. Okay, great. State your name, please.
Philip Taylor. Great presentation. I'm starting to learn chemistry as part of civil engineering, right?
Congratulations. I appreciate that.
But I'm also learning biology. One thing I understand, or I think I understand, is that plants cannot directly uptake nutrients, right? They need bacteria and fungi in soils. Until that develops, they have a good chance of dying, right?
Correct.
And so,
although I'll let you ask that to the landscape architect.
Yeah. So looking at these bioretention systems, and you're talking about the plants, but is it really the bacteria and the fungus doing the denitrification? Or rather than the plant. And as the plant grows, unless it's removed from the system, you're developing a biomass load.
Mm-hmm.
So my thinking is not wrong then, right? You're absolutely right. An ideal situation when you do maintenance, you have to remove some mass.
The above ground structure that we see that we label plants is a surrogate for massive amounts of microbial fungal activity that is doing a lot of that conversion into ways that the plant can uptake it.
Right.
The plant is going to be what incorporates it and retains it.
Right.
But the biomass is in there, which is what gets interesting with our system. They tend to come in, at least in the ones we were looking at in Lancaster, they come in and they chop it down, but they don't dig it out.
Right. And that's kind of what they should be doing, right? They should maybe be removing that and
I don't know because it gives you a good start to next year.
Yeah, what I'm getting to is there a maximum point where you go, I've got too much biomass?
That's a good question. I don't have an answer for it. I really don't know.
Thank you.
I mean, in some respects, they are limited by, well, this one we were looking at, it's limited by the fact that kids climb through it. So they tramp down and kill things. We have deer that eat on it, and all sorts of other things going on. I don't know, I've not seen anybody, maybe somebody else in the room. There's a lot of good researchers in here and online who have done work to look at if there's too much biomass in a question. I don't have an answer. I mean, I'm sitting among a great group of professionals. You guys have done tremendous research up here and online through Minnesota and all that. It's like, I'll toss it. I'll punt that question. Can you ask one I can answer?
Does anyone have an answer for Shirley and Phil? I don't. Sure.
Paula Kalineski. Just listening to the last question though, and thinking about removing biomass regularly, I know, I'm really into my native plants, that little bit that I have in my yard, and I used to cut them down in the fall, but now I leave the biomass until the spring because that's better. So I don't know if that's a practice anywhere or if that would make any difference in terms of the mitigating any delay in the spring with plant growth, but maybe somebody could address that one.
Well, I can answer a little bit of it. What do I call myself? The casual homeowner? I am slowly having my yard convert to clover, dandelions, etc. because I don't go fertilize and I don't go put pesticides on it. My neighbor who has an active contract with Roundup, however, does spray our property line because he doesn't want my clover in his yard. I don't try to, I mean, the last cut happens in typically October, November, and we don't touch anything else. I've not measured runoff from it, so I don't know. We do know that in some locations that are getting road salt, if we don't go to salt tolerant plants, we've got a problem. So leaving it in certain places, leaving biomass in certain places are going to cause problems. But is that going to be, how much is it going to be? What are the challenges? That's a little bit of what we know. But otherwise, those are interesting questions of, do we leave it? You know, my campus leaves it. Lancaster chops it down, but doesn't take out the root mass. Does that dense root mass that springs up next spring limit the amount of new growth that can happen? Because then they don't have to go out and replug it and replant it. They certainly have had to go out and do some of them. That with replanting, they occasionally, there's one by a brewery that where cars periodically land in the bioretention system. We haven't figured out how they jump the curb. They've done some really interesting things. One guy parked in one in order to run into a pharmacy for pick up a prescription, and had a curb height of about that high. So, yeah, a friend used to work for them. I have several friends down there now still. And she calls me. She goes, "Yeah, we got a car in the bioretention system. I got to go out." 3 days later, it's like, "Yeah, we got a car in the bioretention system." I'm like, "That was 2 days ago." She goes, "No, a new one." So they do have to come back in and replant and replug. There's a variety of things that go on. But the question around the biomass is an interesting one about what should we be doing for winter maintenance or some fall maintenance to come in. And that's a really interesting question. Oh, Craig. He's going to ask a hard one.
Fantastic presentation, Shirley. And I've been thinking about how I can ask this so that it is actually answerable. I'm trying not to make it a difficult question, but I mean, I just agree 1000% that bioretention is a game of optimizing multiple parameters. And the way I can think about asking this question, do you think it's possible to get that difficult of a decision-making process into like a specification so practitioners can actually optimize all those different variables? I know it's a tough one. I mean, like, how do we do this? I mean, because clearly, you know, it is kind of a game of whack-a-mole. You know, some things have benefits, some things have drawbacks. Like, how do we get this into, or I guess the how is the difficult part.
Payback for me not having time to participate in the committee, right?
No, it's not. No. Just is it possible? Like, do you
can we do better? Okay, let's come in and let's ask a question. Can we do better? And I say we can. Here's what I'm going to tell you. We are not using all the data sources that we have. Okay, so we have a lot of data, for example, the National Stormwater Quality Database around multiple pollutants at sites by land use. So while we may not be able to predict, unless you want to go out and monitor it, what is the runoff coming into a specific site. We can't, you can do that. It's gonna be expensive. The Boeing out in California does it regularly. Also have to monitor for radionuclides. We could better understand what's coming in within a reasonable range. But even the National Stormwater Quality Database, we've got a lot of range of values. We can also pull out a BMP database because they're measuring influent quality, but they often don't measure it for a lot of parameters. The MS4 permits actually required a fair amount of monitoring. So we have some ideas of what we could get, at least as what is a typical, and Rob Traver in Pennsylvania is starting to put it in as at least, unfortunately I don't know a lot with the industrial, but what is a typical urban runoff from different land uses? That would help us begin to make certain decisions. And then we could flow chart it. I think we can reduce the variability. I'm not going to say we're going to get it within an order of magnitude, but if I can get rid of 3 orders of magnitude and get it down to an order of magnitude and a half, yeah, I think we can. And I think we might have the data to begin to do that. And hopefully, again, if we can get, if any EPA is listening, send money to somebody to start pulling out the data people have got from monitoring into additional and updates to these databases. We really, really need that. So, for example, when I started doing this work around media, I went to Jane Clary at Whitewater and said, we really need information in the BMP databases, not just called bioretention, but can they give us media specs? And so they started asking that question. Can you also give us much more of the design information for the watershed or the drainage area? Not just air, but can you give us percent imperviousness? I mean, it's simple stuff that we could begin to. My goal always is to try to take the very complex and get it down to the very simple that can be implemented. I work in a state that has 1,600 municipalities because we're a commonwealth and everybody has to have their own little home rule of 10,000 people or less. We have villages of 250 and they have to have a permit and they have to implement stormwater management. They don't have the staff, they don't have the capabilities, they need very simple design specs. So how can we take that? That's what I'm trying to do, is figure out what are those parameters that we can relate back into improving performance. We know we had a higher metals concentration. Maybe we want to balance out the nutrient lens. Do we know, if we know what our nutrients are, do we think about what our phosphorus ranges are in our media? Those are simple things to do, but we don't do it as well as we should. And we have some of the better data to do it. But it still is a challenging, because that data is also variable. And we have to accept there's a variability in there we're not going to solve.
Fantastic answer. I agree with everything you said.
And if I could get
appreciate your optimism. We can't do better.
If I could get it, there would be a model in my dissertation that would have worked instead of it crashing.
Thank you so
I'm
much.
still trying to solve it 25 years later.
So we have a question from online.
Our first online question for today is from Chelsea K and Emil S with the Aitken Soil and Water Conservation District. Is there a point in the long term where the soil and the buffers take in so much salt or other pollutants that it harms the health of the soil and plants? If so, what can you do about it?
So, well, yes. I mean, Lancaster managed to kill a bunch of plants for expensive amount of money. And that's when they went out and got dune plants effectively. They were not like another colleague who went and took them with his students. They actually went and bought them. But anyway, so about that, there is a point, again, that's where the plants that tend to be more salt tolerant are going to be critical if you're in an area with deicing. There is going to be a point at which they can't tolerate it. The question is going to be, with these annual cycling of salty water and then clean water that does some flushing, are we going to build up to that level? Yeah, I think we are. There has been, it's not published, it's online, but it's not published as a peer-reviewed paper or anything. There was a project over in Wisconsin where, I've forgotten who did it. I have to go back and look at it. I've got it somewhere hidden on a drive on my Dropbox, which is several terabytes. Student project where they actually went out and they looked at basins that were failing and they did salt content measurements of the soil. And I forgot what the numbers were. I'm sorry, it's been a year since I've looked at it. I can get that answer back to people. And then they looked at, because what ag people do is they actually incorporate gypsum. What they're trying to do is change the ratio of calcium, magnesium, and sodium to restore that infiltration. Because there are agricultural soils have salinity levels and ratios of SAR or like on the other ESR, exchangeable sodium percentage, which is basically the same calculation with a different way of putting the numbers together. It's the exact same calculation. One of them just squares it, and one of them puts the square root in. Seriously. That we know where the agricultural soils fail. And they know if they incorporate gypsum in the soil, a lot of the soils will restore because you just change the balance and you'll get back some of the infiltration. When they tried it, they were, again, student project. Some worked, some didn't. So the answer would have to be, is what they did, because they were students just trying something, is there ways we could improve on what they did to try to restore it? So again, could we add quick lime or something in the spring that would improve it? That's an interesting question, but then again, what does something like that or those do to the plants? And I'm not a plant person. So, but I do know we can try to restore it, but it isn't always successful. And I think, Andy, am I running out of time or?
Yeah, okay, thank you. Randy, we're gonna have to go with somebody else here.
Randy will ask it later today, I know.
Later in the day. But thank you very much. Let's give Shirley a round of applause.
I'd like to thank the audience. It's always good to have an attentive audience.
We'll
Usually
be
my
back
students sleep.
We'll be back in 5 minutes with the panel.
Things have evolved quite a bit over the last 2 decades as far as what you see nowadays is a lot more consistent. And I think the Stormwater Manual has really helped provide more continuity. In the old days, you would review things like, I don't know if that's going to work or not, but they proposed it. So I guess, you assume a lot of assumptions were taken into account maybe back then. But yeah, so that's all I have for now.
That's great. Thank you, Lani. Our next panelist is Janna Kieffer, who is a senior water resources engineer at Barr Engineering Company. Janna, from your perspective and experience, how do you relate to today's topic?
Thanks, Andy. Yeah, so I do a lot of stormwater management, primarily for watershed districts and cities in Minnesota. And really I began my career kind of around the same time that bioretention was becoming, more of a common thing. And so it's been pretty interesting to see, throughout the years how the things have evolved, with whether it's related to design, the regulatory aspects of it, as well as just, I guess, the research and just the overall acceptance in the stormwater community of this as a practice. I've personally been involved on the, I don't get into the details of the design necessarily, but sizing the basins, evaluating the infiltration potential, modeling the volume and the pollutant benefits, evaluating their effectiveness once they're in the ground, both at a site scale and then as it relates to the downstream water bodies. So I've had a chance to kind of touch a little, several different pieces to the bioretention puzzle.
That's great. Thanks, Janna. So I won't ask for Shirley's relation. She gave us the keynote and set the stage for our conversation today, but I will start with an opening question. Please have your questions ready. We'll take questions both from the in-person audience and the online audience. If you're online, please post your questions in the Q&A section of Zoom. But our opening question today is, can you give me one or more challenges you faced when implementing or attempting to implement bioretention in rain gardens? And this is open for anyone to start.
Well, I can certainly start with that. I could think of a handful of challenges, but as the landscape architect, I will say that plant establishment is a huge challenge. Funding long-term maintenance, funding for that establishment period. There's different requirements for each of those phases, and making sure that people understand what needs to be done and have the resources to do so. When you get a bioretention facility that's built and then it gets full of weeds, people don't resonate well with it. It doesn't, serve as a good example of what we want to achieve. And it also probably is not as functional as we want it to be.
Others?
Yeah, I guess I would say most of the bioretention basins I think that I deal with typically have a drain tile in them because where you're capturing the water, usually your soils are tend to be more CD in those locations. And then to outlet, that drain tile is a lot of times you run into limitations as far as you're already connecting maybe to an existing system or a storm sewer system that limits how much media depth you can have. It's so that's a challenge. I think the desired amount is closer to 30 inches or somewhere in that range. And then if you physically can't get that, is that acceptable? Some maybe more questions than answers, but I guess those are some of the constraints that you run into as a designer.
Other challenges.
Sure. Unfortunately, I have a long list here. So I think when it comes to bioretention, it sounds like a simple thing that you're going to do. You're going to, build a depression and put water there and put some plants in it, and it's going to work. But I think really, I've learned that the devil is really in the details on designs, not only on design, but then also how it gets constructed. And so from the engineering perspective, some of the things I'm thinking about is the right amount of water getting to the basin. Have you sized it right? Can you design your basin to not get over flushed when we get these, bigger events? Can you design it offline? Can you, once it's constructed, does the water actually get there like it's supposed to? Sometimes it doesn't. And, as with regard to infiltration, that doesn't always happen as you planned, right? And so do you want to always infiltrate first, but do you have a backup plan when you get out into the field and it's not infiltrating? And then how does that change how does the design, and if you have a drain tile, change your contact time? Because if you're sending water through too fast, as Dr. Clark indicated before, that can be a problem too. So there's just a lot of details to iron out as you're working through these. And then as well as with plants, and you've got to figure out, well, you need it to be water tolerant, but you also need it to be drought tolerant because we have that, and we're just getting more of that, it seems. And so there's a list of challenges, which makes it fun, I guess, in some ways.
Truly, I understand the fun part of it. I find it fun.
That's where researchers kick in, right? Is where the challenges are there. Then we try to do research to try to address the challenges as best we can. What questions do we have from our audience for our panel today? Sure.
What about the economic challenge in an ultra-urban environment where property values are extreme, and having a large footprint treatment approach is something that really comes up against economics?
Well, I'm thinking of, projects in Minneapolis now are doing linear bioswales along each side of the street. So each homeowner is getting a small chunk of a much larger system. Bioretention is a really economical option compared to some other options out there, such as underground storage. And I think it is preferable, especially in an urban environment, because you're getting extra benefits like pollinator habitat and urban heat island reduction. So I'm always, encouraging people to consider bioretention first. But then you do have that consideration of, well, it takes up space. And so if you need that urban space for parking or other surface programs, then you have to do that give and take.
That's a good question. I think of especially cities like Minneapolis, St. Paul, where reconstructs now are requiring the water quality volume, and are you going to take away a tax base in order to put in it's a trade-off, water quality, that's an interesting debate there. If you do go underground, at least if you try to stay within the right of way, you can maybe avoid buying property. But that, creates other constraints again. Do you have the depth, or, with your practice, whatever you're doing, to outlet that, or whatever you're treating. But it's a major issue, I think, going forward, as far as trying to meet the regulations, especially if there's a watershed involved that requires that. How are you going to do that? But yeah, that's a ongoing issue, I think, for the future.
Yeah, I think it's an excellent question, and it's something that I worry about this because, you know, I think that I do a lot of development review, permitting reviews of so, and many of the sites are going underground, maybe even most, at least commercial sites. And so, you know, I think there's some, you know, bioretention, you know, surface bioretention has so many advantages to going underground, but the economics are really more challenging. And so it's something for our stormwater community to think about and talk about in the upcoming years. You know, it's when you go underground, it's hard to know if it's working, but a lot of money is going into it.
And I think too, we have examples locally and elsewhere where they have implemented green infrastructure and rain gardens, even in downtown Minneapolis. You know, we see some of those along the streets. And I think some of the challenges that you all mentioned in the first question are exacerbated in those situations because they're tighter corridors, they're smaller, there's a lot more impervious. They're in some ways even more flashy in terms of how quickly the water rises and even possibly how much longer they are dry. So there certainly are challenges, and we always have to weigh the benefits against the costs in all of these situations. What other questions do we have from our audience? We got lots of them in the room. Oh my goodness.
Down the row.
Better get Randy.
That's a new descriptor for me. So I'm Randy Neprash. Shirley, your data showed that bioretention has problems when it gets hit by a lot of salt. It's tough on the plants, some metals mobilize, but then it also showed that they lose a significant amount of function in the winter. So my question is, where we are placing bioretention, accepting drainage from major roads where a lot of salt is inevitable. Should we be designing them or retrofitting them so that the drainage to those systems are bypassed during the winter? We just send the water downstream and we keep the drainage out of the bioretention during the winter.
I see the questions come back from last night's dinner. Yes, you did. It is a very interesting question. And let me preface it in a couple of ways. First of all, we're going to be adding a lot of things to it to take it offline in the winter. Places are doing it. That is happening. The places are taking them offline in the winter. We are often using more salt as the public is insisting that we get down to bare pavement. There's a public expectation in that, which means that we're going to send that salt slug to our streams. Now, we are sending it during the winter when we are not in the very sensitive stages of like juvenile fish. You know, so we are going, and a lot of our streams have unfortunately adapted to slugs of salt in the winter and have recovered in the spring. So there is some argument for that. We can get some, and we saw it in the data, we can get some reduction in the salt concentrations if we actually run them through there and use them as a filter to try to capture some of the salts. Other possibilities could be to change out the salt in some areas to something that's a little bit more reactive and a little bit less harmful. So there's a lot of options in that one. So should we take them offline? I can see a lot of problems with that happening and not being done well. But for some of it, I do get, I get the idea, because again, I get more concerned about sealing the soils and not getting the infiltration, and suddenly having our piping systems, our streams, et cetera, getting a much higher slug of water and intensity because it didn't go through the infiltration we thought we did, and we start seeing blowouts there. Probably my better answer for that is the unintended downstream consequences. We're basically creating a little parking lot type ceiling on those things.
Other thoughts on please?
Would you like to take them offline, or?
I know that I've worked with some clients in the Toronto region who are doing this. and are really concerned about that issue. It's another operations and maintenance consideration, and I think it's really challenging, especially in the spring. When do they come online? When's the right time? It's really hard to know.
Our campus turns our parking lot white in the winter with salt.
Yeah, but the University of Minnesota is known for.
Well, and I didn't highlight it in the graph I showed, but there is a point on one of those graphs, that pond, where we had the slower salt decrease, that says students returned to campus, and all of a sudden our campus inlet went way up, because when faculty and staff were on teaching during COVID, they did not care at all. They barely cleaned it, but once the students come, because parents sue.
Well, it is a safety, it's definitely a safety issue. So.
Yeah, well, older faculty and staff, they weren't that concerned about.
Well, and I think it gets, if I could add to the question, Randy said major roadways, I'm thinking parking lots, right?
Yeah.
That's what some of us said here is we have to think about those, and private versus public application. Sometimes our public application has more control and has certifications and training, whereas private application is mostly unrestricted. So those are some other things we have to think about as well. Any other thoughts on that? I'm going to take a couple back here. We had.
Thank you, Craig Fairbaugh again, and perfect segue, Randy. I wanted to focus on something Janna said about taking systems offline, and not offline for treatment, but more separating water quality from flood control, so we're not sending large volumes through the systems. I think that really just adds an extra parameter of optimization that makes it really difficult to perform water quality when we're sending large storms through the systems. I think it's a really easy thing we can do to improve water quality. I just love to hear everyone's thoughts on, we ask Bioretention to do a lot of things. And I think if we kind of separate out flood control, especially thinking about climate change, I see a lot of presentations where they're using Bioretention for, dealing with larger volumes from climate change. And so I just love to hear everyone's thoughts on, should we really be sending flood control volumes through Bioretention? Is it a best practice that we start trying to move them offline and separating the flood control benefit from water quality?
I mean, I'll start that one. I guess to me, it depends on the site. And I think that's easy, the answer is almost always depends. But I think, when you can design a system where you're taking the amount of water you want and then the rest of it bypasses, I think that's ideal from a lot of perspectives. But there's, in reality, especially when we're retrofitting so much of our infrastructure, it's just really sometimes not feasible, or, I think it's interesting you brought up the relation of flooding and bioretention and green infrastructure. And I do think that, I've done a fair amount of flooding modeling and studies in my career, as well as water quality. And I think there is sort of this general idea that, our bioretention basins are going to help us solve our flooding problems. And I think, at least in the work I've done, when we're talking about the amount of rainfall we're talking about, when we talk about the big storms, it's a bit of a drop in the bucket. And I know that's not a popular answer, but I think it's the answer that at least in my experience. So I think we have to be careful to try to ask too much from those, our water quality infrastructure.
So I guess I'll build on that a little bit, and take it a little bit different. So my question, maybe I won't go back and ask you this question, Craig, but it is an interesting way of thinking about it. What are we trying to achieve? Okay, so I'm going to ask this in this way. If we divert water away, and there are people who are proposing it, Rob Travers one is trying to put it into a manual to talk about diversion. Philosophically, I think it's a good idea. Let's protect the systems. But where is it going? Are we going to divert it straight to the stream? Or are we going to ask for it to go to a basin for potential treatment? Then that comes down to the cost of losing the land for building and development, or the cost of trying to retrofit something either underground or ultra urban space, or any of the other things that could go wrong. Now, some people will say, well, we take the first flush through the system. But in a lot of places, we're not seeing a first flush because it's tied to rainfall energy. In a lot of respects, the pollutants that wash off on certain pollutants. Certain pollutants do not have a first flush per se. It takes a little bit more to knock them off. And so then we need to capture the heaviest part of the storm to get the water quality. So how do we deal with that? Then that's a control sensor issue. And that's a lot of controls to be out there with the random public. So, what do we want to do? The goal of the bioretention is to treat as much water as we can without failing the system. either causing permanent damage or not getting the treatment we want. So how do we figure out what part of the storm comes and goes, and how big is the system? I mean, I've seen some developers will put in a large bioretention system to take a neighborhood, you know, and that's not really its intention. It should be a much smaller system, much smaller site. So it becomes a real debate about that. What do you want? If you take the first flush of water, that could potentially be cleaner, and you miss something when you get a really heavy downfall and you move a lot of sediment. So it's a real challenge.
So it actually triggers a couple things in my mind, and we will be discussing funding in a future seminar series, but thinking about stormwater and how much funding comes into stormwater versus things like wastewater or drinking water or other sectors, it seems to me at least, we have a strong lack of funding for how much we expect these systems to deal with and do. There is more funding and becoming more funding for climate resiliency. So if people are looking at separating their flood control, their water management, volume management from some of their water quality, there are some more funding on that. And there is more general stormwater funding as well. And as I said, that will come up in a future seminar. But, you know, one question I want to ask is you know, out of the things we've talked about so far, what other lessons have we learned? What other lessons would you share, you know, related to these topics and maybe others related to bioretention you want to make sure that the audience gets a chance to hear?
I think it's important to put in under drains if you have soils that are not, you know, if you're not sure they're A or B, why just to make sure that thing's going to drain down. At least you have the option to open that up to make it work. Otherwise, you know, you've put a lot of investment in something that's really not doing anything worthwhile anyway.
Can I dive in on that a little bit? So let's talk a little bit about under drains versus infiltration, because there are certainly some places where infiltration is really difficult. I mean, there's some areas where you have shallow bedrock or shallow groundwater, very, very tight soils that limit infiltration. But I've seen designs where they create storage that allows long-term infiltration within the media and not forcing all of it to come out through the under drain or bypassing. So I don't know if our panelists can kind of comment on that, infiltration versus under drains. Do you make other design changes when you have under drains in terms of thinking about the media? A lot of what Shirley talked about is things that can come out, whether it's salt loading or not salt loaded. Many of our common designs can export some nutrients and other things that we might not want in our under drains, ultimately getting back to surface waters.
Yeah, I mean, I guess I'll jump in. I mean, I think usually from a design perspective, in most cases, I've been working on infiltrations preferred, and you're gonna get the volume reduction benefit there, and you don't have the under drain with the pollutants are just going down. It's fine. It just goes away. It's magic.
Yes.
You know, and obviously it's not. There's that stuff that can you know, leach through. But I think that I like, as a designer, having a plan B. So, you know, I think because the worst nightmare is when you build the thing and then it's full of water every time it rains and somebody calls you and said, why isn't it working? That's terrible, right? So I guess that's where having a plan B in your design, but going the infiltration route first is the approach I'd take.
From the planting perspective too, we like to be able to operate without the under drain because of course you can have more organic content in your media if you don't have the under drain, and the concern about that phosphorus leaching out that way. Also in city of Minneapolis, they won't use shredded mulch on the surface of any features that have an under drain for fear of phosphorus leaching through that way. And that's really challenging for erosion control and establishing a, you know, secure surface of your feature through plant material only. When we do use under drains, we're usually doing a gate control valve on pretty much every feature so that the operator has more control and then can really see how the system is working under real conditions and dial it in that way.
Yeah, I'll add, if you're thinking about the water balance, some areas are actually relying on groundwater. And while this is, a single bioretention doesn't put a lot of water back into the groundwater, it is a way of recovering some recharge in urban areas that we took out by putting asphalt on top of it. So when my area relies on groundwater, that's our drinking water source, and our wells are near town. So anything we can do to, we're pumping out more than we can replenish, but we are getting that. They just built an apartment complex on top of one of the recharge areas. So, tax base. That's all I'm going to say is tax base. What they say at the council meeting. But that is the thought process, is that if we can do it in places where we can do it safely and not affect foundations and underground infrastructure, infiltration would be preferred, so we can actually get that water balance benefit. But we do have to watch for certain pollutants do tend to migrate, but they're going to migrate to the surface water versus the groundwater, which eventually will show up somewhere. So the stormwater magic doesn't go away. Mickey's got a little problem with that. And I will say, we were working the project in California, and we were talking to a advisory team, and a person on the advisory team who was representing his company said, yeah, so we don't have to have a surface water discharge permit because we just infiltrate everything. And I think it's a challenge of the regulatory authorities also, is that the regulatory authorities separate surface water and groundwater in a lot of places, and we are not accounting for the interaction. But everything I talked about, we're talking about media design, can turn right back around and apply to an underground system. And if you make some modifications, it can apply to a green roof system, where if you were building new and we're talking about green roofs, you can actually think about, greening the urban infrastructure with something that's on a roof instead of in a curb cutout, or at least getting some additional area. So now retrofit's a lot harder because of the structural issues.
Let's take another question from our audience.
Set that row up.
Let's go down the line. I'm Jeremiah Lehman. So Shirley gave us a lot of information about all the variables, or many of the variables that go into making bioretention function, right? Another one, a large one, certainly has to be long-term maintenance. So given all individual perspectives and just the fact that we are taking bioretention and putting these small dislocated systems in all over the place as much as possible, what do you think are some of the key considerations up front to ensure that long-term maintenance happens and happens effectively, and you have as much longevity out of your system?
I'd say staff training is a huge issue. Cities turning over to implementing a lot more green infrastructure, and the staff is used to taking care of pavement. And there's a huge hill to climb in terms of getting everybody up to speed on what this is about, what needs to be done, and how it's supposed to operate, and what is important to do to ensure that it continues to operate effectively. It's a whole new paradigm, a whole shift in thinking from the municipal operations perspective.
Yeah, I would say the long-term maintenance agreements, especially for developments as they come in, that hopefully would take care of most of that maintenance, concerns.
And I think, if it works out, depending on the situation, if you can have the maintenance team in the room while you're designing it, I think that's great. I mean, I think there's a lot of decisions along the way as you're designing these facilities related to pretreatment and a lot of, outlet structures and all these things. And if that person's at the table and can be like, oh, well, I'm just going to bring my truck in here, and, it can really influence design in a way that, makes it easier to actually do the maintenance. And because sometimes if it's tricky enough, it's just going to, oh, I'll do it next year. So.
Well, so if I can add to that, you all have much more cooperative people. So and I'm going to clarify that, because when I think about it, and a lot of the things we talk about are going into municipalities because that is a public works feature, and they've kind of got an obligation that's built in to maintain them. But there's still a lot going on private land. And so what you've got is you've got a developer that gets the permit, does a notice of termination, turns it over to the client, who then may turn around and sell the lots or do something else, or may sell it later. And what we've seen is that second transfer that often is the problem. There may be a maintenance problem with the first one, but it's the second one. So what our people are talking about at the state level as well as localities has been deed restrictions. Has been actually going into deed restrictions and putting long-term maintenance requirements. Oh, and you can't fill that sucker in either. Because that's happening. Because it's like, well, there's this depression in my front yard. I don't like it. So I'd rather have it be a raised bed garden, which doesn't do anything for stormwater. So again, it's that issue. And other places are choosing to not mandate anything on private property, that everything goes to public. I mean, so there's a lot of challenges in the governmental sector that I think they're still struggling with, that I keep hearing about from people. But I know Pennsylvania, we're starting to see some of them go into deed restrictions. HOAs. The HOA covenants are also kind of interesting with that.
And we've certainly seen that locally, where rain gardens have gone in, they've been on semi-public, semi-private property, and the private ones can disappear, you know, if you don't have any legal recourse to protect them or keep them in place. So I actually want to build off a comment that came in, and the staff training. Britta, you mentioned staff training and making sure people are trained properly. And the question I want to ask is, okay, staff training, true. What about citizen training? And what about, you know, how can we enlist more people that can help, that aren't focused on just the streets or the curbs or the gutters, you know, and that maybe would be not only more willing and motivated, but might even already have a green thumb. So what about citizen training versus staff training and to help with the maintenance?
I think that's hugely important, and definitely something that needs to be cultivated. And it is.
Well, she is a landscape architect.
And a big part of the work that I've done with the city of Minneapolis is that sort of public outreach and education, and getting people to understand what these are for and how they can help. And a lot of people are really interested. I mean, people in Minnesota care about the environment and want to be a part of this. And then another thing is, I've seen some great success stories with cities putting curbside bioretention around different neighborhoods, and then getting agreements with the homeowners in that are in front of those installations, that they're going to do the maintenance, and then they take great pride in that, and then they look really good. And you know, with a little extra education on how to garden in bioretention, that can be a really successful partnership.
Other thoughts?
This goes for this question or the previous one, but I think when you're designing these systems in the plant palette, you know, I think simpler sometimes is better when it comes to maintenance, especially when you're asking other people to maintain. I know that I can't always tell what's supposed to be there and what's not.
Right.
I would add to it, the other place we're seeing going in would be bioretention in school areas. And they're actually getting the kids out to help plant and maintain. And so you start young, and then they take that, you know, recycling happened a lot because kids went home and told their parents what they learned in school. And we start thinking about where the next generational change helps push things through, because they're actually learning. They learn about plants, they learn about science, they learn about water. And, you know, they bear some responsibility. You know, once you pull the backhoes out, the kids go out and plant, and they're happy to plant plugs. This is great. You know, it's kind of like how when we were all kids and they brought the TV, roll the TV in. It's like, hey, a day without a teacher and a chalkboard. You know, you go outside. But it's amazing how much learning happens, how much education can happen if we do these kind of things and think about how to involve our kids. Not by they all work for pizza.
Pizza, that's right, food. And you know, you can make that very approachable. I've seen some guides where for homeowners and public that you create a design with 3 species, and you have a photo guide to be able to quickly and easy identify what should be there. And if it's not one of these, it doesn't belong, right? So you can make it simple and make it easy for anybody, and you can make it more complicated. I think there's others in the room that have wanted a design for their yards or their rain gardens that were more complicated than the local suppliers could provide even. So it's a full spectrum.
City of Lancaster, one of our people who supported us through this research actually sat down and developed a full schematic, not just the picture of the garden, but here's how you figure out the slope. Here's how you do this. It's actually a real simplistic guide. You could build your own, bioretention and drainage to it on your yard. And then what do you need to go when you go to the big box store? But it's not just the plants, but it's the slope, it's the size, and all that based on your roof area. So she actually really simplified the design down to try to encourage it to get more bioretention onto properties, including how far away from buildings, et cetera.
Any ways that we can simplify design and ease maintenance will make sure these things will function better in the long term. What other questions do we have for our panelists?
Hi, my name is Mark Deutschman. I'm curious, like when I saw Dr. Clark's presentation, she presented a whole list of contaminants, right? Obviously, they all behave differently in the environment, and you also presented a whole list of processes.
Mhm.
So my question is, are we expecting too much? So you have different contaminants with different processes biogeochemically. Should we be stealing stuff from the wastewater engineers where we have a treatment train approach where initially it's maybe sedimentation followed by, adsorption, realizing that you have space limitations also often in retrofitting, but I know it strikes me maybe we're expecting a little bit too much.
So I'll take a crack at that answer. I kind of steal stuff from the wastewater and the industrial treatment industry on a regular basis. If we're getting high sediment loads into these things, yeah, you really do need a 4-bay with treatment. A lot of the good designs already build a small 4-bay in that's easy to clean so that you can get rid of the sediment. We got to figure that's a flash sedimentation, so you're probably only good down to 20 to 25 microns. They're just not retained in there that long. And you got to watch for scour. But yeah, we're doing a lot in there. The treatment train approach is one that I've done a lot with, mostly underground, because trying to do it in things like public works yards where they didn't have a lot of space. But yeah, the treatment plant, bioretention just is a treatment plant kind of condensed with it all mixed together in pore water. So if you think about it that way, there's a lot of sedimentation, surface filtration going into. You're also then looking at biochemical processes. So there could be some thought to separating it. Again, it's a land use area. Others like this idea. You got a pretty amenity, and there's a value to that amenity to having something pretty to look out the window at. I would say on industrial sites, and I've done quite a bit of work on industrial stormwater, that you almost have to do. Is you almost have to separate those two, particularly if you're talking about outdoor industry. I've done work around scrap recycling, and that you almost have to, because you've got to protect the treatment process. And that's got to have to require sedimentation up front so you can get it down to something you can deal with. What I would say is the project we were doing out in California, what we did was we had the permit, and then we had the influent data, going back to the question that came up earlier. And what we did was there were a lot of different pollutants in the water, several things in the permit. What we tried to do is we went through and we kind of matched up what was already, even on the runoff, already was below permit level. So we didn't worry about that as part of the optimization. But it required us, then we came down to from about 50 things down to about 8 to 10. Which ones were we violating and how often were they being violated prior to the design and installation of these bioretention systems? And by doing that, we still got everything from nitrogen to dioxin to strontium, but we didn't have radium. But we didn't have, I forget what the other one we didn't have phosphorus. So we didn't have suspended solids. So again, it required some localized knowledge, which does cost money to get that data. But then we were able to say, given this multi-parameter optimization design, we weren't designing for everything. We were designing very specifically for a smaller suite of pollutants.
All right. Do we have a question in the back too? We'll take one and we'll come back to you, Randy.
Hello, I'm Grace. I'm an undergrad research assistant here at SAFL. We talked about engaging with a public that's eager, but Shirley, you mentioned in your presentation your neighbor who has a contract with Roundup, essentially, and that mindset is very prevalent back home in my community. So I want to know if you've had any challenges with a public who doesn't see any benefit beyond a single species manicured lawn, and how you've overcome those challenges.
Well, I haven't overcome them yet. He's using a little less Roundup. We haven't had a long conversation about that. I just refer to him as Roundup Man from the window. Overall, they say that the public outreach, and I think any one of us up here on the panel can probably talk about some of our public outreach events about trying to talk about the multiple benefits of these systems of changing lawns. It's going to be an example because, again, you think about how we've been acculturated or acclimated. The status symbol is you've made it when you can have a monoculture. If you have the luxury and privilege of not having to grow your own food, and you don't have to have that's the sign of being wealthy. And that's a mindset that's coming. Nobody will say it out loud, but if you don't need land space to grow food, you are wealthy. And that's been where we are. There's also been manicured lawns that drove to the castle, to the temple, that also then where our connection to whatever religion we're in, what deity would tell us things. This goes back millennia. What are those status symbols? And they've carried down. Now trying to get us to understand and break that mindset. My new chancellor who came in a couple months ago is a little bit more amenable to thinking about native plants, even short prairie grasses that don't have to be mowed that often. Well, I don't know what we're going to do with our landscape staff. Because again, we've got too many, they have to deal with grass. But the one before, it's like, well, parents won't like it because the grass is too tall. And they might think that there's going to be a rapist hiding in the bushes around their daughters. It's like the grass is going to get that big. Like, I don't see the size of this. But we had a long conversation about this because he very much had a mindset that an appropriate university looked like it was dropped out of Oxford, England. And it's just slow changes. The thing I love about working with kids in elementary schools is that's the generation we've got a mindset we've got to change. And we go from there. Otherwise, you start getting into away from carrots and into sticks. We're not going to put phosphorus in the fertilizer, or we're not going to allow you to do this or that, or there's a lot of things that go on, but it ends up being what people feels a punitive approach.
Yeah, certainly not everybody is embracing and ready to go, but you have to work with those people who are and make an example of how it can be a good thing and slowly spread that out across the community. I think you're absolutely right. The monoculture is a dominant aesthetic, and something that this is what we're doing is really kind of butting up against. And so some people say, well, can we just have turf grass in our bioretention? Some bioretention facilities could support turf grass, but turf grass doesn't have the deep root systems that are really going to make it the most functional system. So it's not a truly functional bioretention system. So I've been working on developing different types of native seed mixes that are utilizing the most kind of short, not offensive looking, wild looking plants to see if we can develop some sort of mix that meets people in the middle, does what we need it to do with the roots, and looks in a way that's not offensive to those people who are still married to the concept that the trimmed monocultural aesthetic is the way to go. So it's an ongoing situation.
Other thoughts on that? Looks like we might have a question online.
One question online. And this is also related to citizen involvement in upkeep. Can we get our cities to update their ordinance to make boulevard green infrastructure a resident responsibility, similar to how they have to mow the boulevard grass? I think we would see way more boulevard green stormwater infrastructure if residents took care of it.
One thing would maybe be is to have an incentive for them to do that by maybe reducing their stormwater utility fee or eliminate it. That might be quite a change.
Other thoughts?
I think it could be a challenge for people. I think there's some benefits to having a unified approach and trained staff at the municipal level who can do it, but certainly an option to consider, and it has worked well in some of these places that I mentioned previously where there are inked partnerships with certain homeowners who are willing to take on the responsibility.
And I have seen it both ways. I've seen it where people have had success, where the homeowners will take care of things and do the maintenance properly and appropriately and regularly. I've seen other instances where they don't, and then either the city or the watershed district will assess that property or those properties that don't. So there can be a carrot/stick associated with it.
So this is right along the same lines, and typical of me, it's not a question, but I'll ask you to comment on it. It's a story of a city in Minnesota. So it's Maplewood, which decided like 12 years ago or more that they really liked rain gardens. They also had a cycle of neighborhood street reconstruction projects. So it's like a 20-year cycle to go through the whole city. But in the planning and public meeting stage, for every neighborhood reconstruction project, they would go in and they would educate people and offer them a legitimate choice. You, the neighborhood, can choose to have your streets reconstructed with curb and gutter, or no curb, swales, and lots of small rain gardens in your front yards. Almost all the neighborhoods, to the best of my knowledge, chose no curb. And the end result, last time I checked with Maplewood, which was a number of years ago, they have more than 800 rain gardens in the city. The city owns and maintains less than 10% of them. They've been doing this for more than 10 years. So my guess is it's working. It seems like a remarkable story all by itself, but it's kind of the answer. You give people a choice, you get them to buy in from the beginning, and you've got a really good chance, without assessing them, without forcing them to sign stuff, that they'll take care of them. It just seems like a lovely tale.
Yeah, I can attest to that. I live near Maplewood. I drive by and admire their rain gardens all the time, and they have a great program. They have a lot of homeowners who are doing great work, and Maplewood should take a tour of the state and teach us all how it's done.
I believe they have very good soils though. And so
It doesn't hurt.
yeah.
Good citizens, good soils. Exactly. That's what you need. Let's take one more audience question and then we'll move into our close.
John Gulliver. I have a statement to make about under drains. I feel that over reliance on under drains is the bane of bioretention systems, because we have found that what they do is they increase the orthophosphorus coming out by an order of magnitude. Typically, that's what we have found. And phosphorus is very important in Minnesota because we have so many lakes. So we have been advocating capping all the under drains. I have no problem with a capped under drain. And sea soils can infiltrate water if you have the right plants. Not D soils very well, but sea soils can. So my question is, what do you think about that?
I guess I'll jump in on, I think when I talk about a plan B, I think that, right, like having an ability to have an under drain, but capping it unless you absolutely, doing everything you can to get the infiltration out of the site is really, I think that makes sense. Cause I think it is, you do get more benefits out of that sort of, so capping, I'm good with capping the under drains unless you absolutely need it.
I feel like as the landscape architect here, I can be more cavalier, and I'm like, just get rid of them. We'll deal with it. I think that they often perform better than the modeling shows in real non-underdrained, and that they, like you're saying, sea soils will infiltrate.
Yeah, well, I see it as basically as a backup. similar to like an overflow, that if it's holding water, I think of one that I bike by, and I watch it, especially since we've had a lot of rain here recently, and I just went by it on Sunday and it was full of water, and I'm wondering, is this thing gonna drain down, in 48 hours or not? I guess I should go by it again here and see, but if it's standing water and we keep getting more and more rain, then it's just gonna flush through. Yeah, I guess if you have it open, at least you're going to get some filtering through there, but yeah, will it just flush the pollutants right through? I suppose it probably would.
Well, and the question is when is it failing, right? If it's raining, every day or every couple of days, we don't even get to our 48-hour drawdown time period. So maybe we aren't necessarily needing to expect it to draw down. And those are just storms that are outside of our design criteria, right?
Getting some rate control out of it.
You certainly are.
Open, so I guess that's the one benefit.
For sure. Other thoughts? I do know too, if your rain garden has healthy vegetation, if it's vegetated and has healthy vegetation, that helps a lot with getting water through that surface and into the soils. And even if you have poor soils, if you have deep-rooted plants, they can really get water into the soil and make it disappear. So
I guess I will just add, there's a lot you can do in your design process and even during construction to get, when you have a site where if infiltration is questionable with the soils, I think it's sort of, again, doing all those things to get infiltration. And then, then if you need to, go to a backup. But I think, even sand trenches or soil mitigation and there's a lot of different techniques you can use to get what you need out of your site. So.
And I think if I piggyback on that and on what John said, I think some of the techniques that we're using today to determine whether or not our soils are good for infiltration maybe are not giving us good answers. They're not giving us good accuracy. Maybe they're more tuned towards whether our roads are going to be stable and heave or buckle or collapse, and not really telling us what the soil can infiltrate. And so that is an area of research that we're working on right now and trying to find better ways to give us more confidence in soils that can infiltrate or not. The other thing to consider is in our urban areas, our urbano soil, as I like to call it, is not what's on the USGS maps or the soil maps anymore, right? In many of these areas that have been developed for many years, it's a very different type of material.
Well, Pennsylvania doesn't even list parameters for urban land.
Right.
So Pennsylvania's web soil survey doesn't even, the USDA punched it. They said, we're done.
It doesn't matter anymore.
But it is one of the things I've actually found. I've also seen designers use surface infiltration rates for design instead of looking in the table and going down the 30 inches.
Right.
So it's actually understanding that you're going to take that out. And, yes, there are questions around soil sealing and during construction, things like that we're trying to mitigate, but it's also, you're looking at the wrong layer.
Right. And that's something where we're looking at, trying to develop techniques you can do at depth where the bottom of the rain garden will be.
Without having to send a backhoe out like somebody in our state suggesting to do. Contractors are pushing back.
Yeah, that's expensive and challenging. And obviously during construction, that's a very important phase. There's really three parts of it, right? Design is very important, construction is very important, and maintenance is very important.
Because the other choice is doing a perk test during evaluation stages, and that is an expensive proposition, and nobody wants to do it.
Right.
So how do we get better? How do we get there?
Many challenges, right? Where we started this conversation, right? With many challenges we have. All right, we're at the close of our panel discussion. So I'm going to finish with this question for each of our panelists, and we'll have them answer in the same order that we started. So what are your key takeaways from today's seminar? What lessons have we learned? What would you like to re-emphasize or highlight from our conversation? Or what new lesson learned would you like to share that we didn't get a chance to talk about? How would you like to close out our seminar? So we'll start at the far end with Britta. What's your lesson learned today or key takeaway?
Well, this is not a new lesson learned, but a key takeaway is that I have so much to learn from all of you who can do the research and tell us designers how these things work. And I've learned a lot from Shirley today, so thank you. And I would just put the plea out there to do more research about the plants. Let's figure out this whole biomass situation and when we should remove that plant material and what is the effective lifespan of the subsurface root systems in bioretention. That's what I really want to know.
That's fabulous. Thank you.
Yeah.
Lani, what's your takeaway?
Two quick bullet points here that from Shirley. Soil compaction was higher in the summer due to the root mass, which that was kind of interesting. And then that the salt compacts the soil, reducing infiltration, which probably should have known that, but just to be reinforced of that point.
Sure.
Janna.
I feel like the presentation really and the discussion has highlighted really the complexity of these systems and that long list of processes that is happening in these bioretention systems. And I think, you know, I think this term multivariable optimization design, I think that's a great term, but that's a lot. That's overwhelming as a designer or as, you know, and so I think it makes me just really, again, appreciate and see the need for more research and then synthesizing that research into practical, and, you know, usable standards for the engineers that are just needing to get this design done without going to your client and saying, well, we're going to do a multi-parameter optimization. And that'll be, yeah. And then, so I think it just, again, that synthesis of the research is important.
Shirley, you get the last word.
Sure. I think, well, at this point, I'm going to give a plug for Craig, who's in the audience, and his media filtration committee, who are trying to actually take a lot of that research and synthesize it down, but also highlighting where there is a dearth of data to make some of that synthesis. And I would also then probably didn't highlight it as much as I should. There's a really good group of researchers in the stormwater field nationally and internationally. I'm sitting among them here. We feed off each other. We get our ideas off each other. We have these conversations, and hopefully by having these interactions, we learn from each other. We can then improve the design guidance that we're helping our states, our regions, and our nationalities put together. I would end with that, and I want to thank you all. Thank you for the invitation.
That's very good. Well, yeah, thank you. Help me thank our panelists and our speaker. And I want to thank you all for joining us today. This will conclude our Minnesota Stormwater Seminar Series. I encourage you to check out our website for future seminars and also our YouTube channel if you want to see any past seminars. We have a great lineup for the rest of 2024. I'm super excited for that. But I hope to see you at a future one. So thank you and have a great day.